Welcome back to the AtroKraft Satisfactory Megabase Project. Last time we locked in the aluminum chain, stood up copper production, and finally started feeding materials through the Parthenon itself. The factory is running, but it's far from finished. In this episode, we're picking up right where we left off, working through the build list one item at a time. It's all about refining, connecting, and solving the little problems that appear once theory meets reality. As we push deeper into production, a few new challenges start to show up. We'll see supply shortages, routing conflicts, and of course, water issues. To keep everything running, we'll build a full bottling and transfer loop to move a massive amount of water up into the top floors, supporting the rest of our pure smelting lines and laying the groundwork for the next wave of expansion. So let's dive in, another day, another layer of complexity, and one step closer to bringing the Parthenon fully online. The first task for today is expanding our aluminum production chain as far as we can take it. We're starting with aluminum casings. Even using the alternate recipe that adds copper, these draw from the same resources already feeding the outclad sheet line. So this step comes down to clean belt routing and a bit of math to confirm that the supply lines can handle the extra load. This skid runs underclock to match our overall production plan, so the demand increase is minimal. Once the belts are in place, we update the signage to reflect the new values, fire it up, and verify that the actual output matches spec. With that confirmed, we route the finished product down into its storage bin, and just like that, another item gets checked off the list. Next up was the heat sink plant, and since heat sinks rely on copper sheeting, that production had to come online first. Our plan calls for 69 copper sheet constructors, which translates neatly into 330 machine skids, each running at 76.6% clock speed. Having roughly a quarter of that capacity idle might sound inefficient, but it's cleaner and faster than breaking the layout into odd-side skids or building custom. Together, those 3 skids consume almost 2 full belts of copper ingots, so to keep them balanced, I built a closed-loop feed system. Here's how it works. Each skid taps into a circulating belt loop that's fed in several places by priority mergers and drawn from at every producer. Those mergers favor the copper already on the loop, and fresh supply fills in only as needed. The loop itself is just a standard manifold with the last splitter connected back into the first through a priority merger. This keeps flow consistent and evenly distributed and ensures that any excess always collects at the end of the run instead of backing up early. Once that loop was stable, we ran our usual capacity tests. Then we confirmed the flow rates and updated the signage to reflect the new numbers. From there, it was simply a matter of duplicating the process for the heatsink skid, routing inputs, labeling outputs, and verifying that both lines ran perfectly to spec. From here, I committed to building out the entire electronics chain, which was easily our biggest gap in production. But that meant we needed to bring in both Caterium and Quartz into the factory. Caterium was actually closer, but it's always better to do the harder thing first, so we started with Quartz. Unfortunately, our options for getting it weren't great. The nearest Quartz nodes were west of the swamp, far from any existing infrastructure. The best solution seemed to be routing the raw quartz from those nodes into the swamp train station and then hauling it the rest of the way to the Parthenon by rail. So that's what we set out to do. We built a raised causeway cutting straight across the swamp, high enough to clear the treetops and hopefully avoid most of the hostiles. Hopefully being the key word here, because of course we didn't avoid them. Still, after a few close encounters, the line was completed and routed cleanly back into the swamp station. Once the extraction and routing was stable, we built a dedicated train platform at the swamp station for quartz hauling. Then headed back to the Parthenon to do the same there. We built 2 new platforms, one active and one spare, and just like that the quartz line was operational, bringing in a steady flow of material to feed the next stage of electronics production. The quartz expansion was slow and brutal, and honestly it didn't feel like major progress at the time. But in hindsight, this was one of the critical hurdles that had to be cleared before the Parthenon could fully come online. It also marked the first time we brought quartz into the megabase at all, a small but important milestone that set the stage for everything that followed. The next major hurdle came immediately, more water. We already had plenty of it, yes, but all of it was down in the bottom of the structure, and the subfloor was already packed tighter than I really wanted it to be. The Parthenon was built with tons of extra space for a reason, and it was time to start using that space properly, so that meant bringing all the water all the way to the top of the base. The main issue here is that Satisfactory simulates head lift, which is the pressure required to push fluids upwards through a pipe. So we had two options: either pump it up the whole way through the interior of the column, spacing pumps the entire way, or bottle it and send it upwards on belts. Bottling is not the efficient option here. It takes more power, it's slower, it adds layers of complexity that can and will go wrong, but it's also the more interesting engineering challenge. So this time at least, we're going to do it that way. We're bottling it all. So to handle the bottling itself, we started by designing a dedicated packaging skid. This was 2 rows of packagers for a total of 20 machines per skid. And once that was together, I adapted it into an unpackaging skid and saved both as separate blueprints, one for each direction of flow. That first version we put together wasn't quite right in the end. I sized the system for 600 water per minute per skid, but later realized it could safely handle 1200 water per minute per skid. So the final revision now runs 2 Mark V belts in and out per skid, with 2 Mark II pipe connections feeding the loop. To prevent the entire network from backing up, each skid pair gets its own industrial storage container pre-filled with empty bottles. Once that's full, I disconnect bottle production and retie the container back into the return line. This way, the storage unit can hold the entire circulating inventory of bottles. This not only guarantees that the system can never clog, but it allows the entire line to be cleared by turning off the packaging skids and running the unpackagers until the belts are clear. For the loop itself, the bottled water rides up the Parthenon's column just like every other material line. 3 vertical lines up in one column, with 3 down lines in another. Later expanded to 6 after correcting the math oversight. Testing fluids is always trickier than solids, since you can't just feed them into a sink. Instead, we tied the outputs into fluid buffers and kept draining to confirm that the system could sustain its full flow rate. Once the readings held steady and no bottlenecks appeared, the bottling loop was declared stable and complete. The Caterium though is still untouched. Luckily no new train lines are required as there are several rich nodes right here in the dune desert. But as usual, I couldn't just run a few belts and call it done. Instead, I took this opportunity to finally clean up the chaotic belt sprawl around the Parthenon. This new Caterium line would run on a neatly aligned elevated causeway set at right angles to the Parthenon itself, effectively establishing the building's grid as a reference for the entire map. We started with the west side of the structure where the Caterium nodes are located and built the first set of structured causeways there. I also brought in as much limestone as possible since the nodes are local to this area. We'll be needing it in huge quantities soon. We did similar on the east side with nodes feeding limestone, copper and sulfur, and coal in the north. By the end of all this rerouting, the exterior of the Parthenon looked dramatically better. The belts no longer sprawled across the sand, and every line now ran clean, organized, and purposeful. It finally looked engineered. And that's where we're going to wrap things up for today. The Parthenon is now almost fully stocked with resources. The logistics network is clean, and we're finally in a position to make real progress on production next time. In the next episode, we'll dive straight into quartz crystal, concrete, and Caterium ingot production, setting the stage for quick wire, oscillators, and the rest of the electronics chain that ties it all together. So if you're enjoying this project, leave a like, hit subscribe, and check out the live stream over on Twitch. Links in the description. Thanks for watching. I'll see you on the next one.